Okay, so in the previous problems we have earlier, what we're given is the equilibrium concentration itself. Okay, so but later on, things will be more trickier because we will not be given any equilibrium concentration. Instead, we will be given the initial concentration rather than the equilibrium concentration. So that will require us to know the direction of the reaction and how to solve for equilibrium constants or equilibrium expressions. Okay, so typically this involves solving for equilibrium concentration and the molar solubility of insoluble substances. When we say insoluble substances, these are most of the time precipitates. Okay, so precipitates do not dissolve in a solution. However, at some point in time, it will. Okay, so it will not fully dissociate into ions because it is a precipitate. However, there is an instance at which your precipitate dissociates. Okay, so the term insoluble is a, let's say, a gross term. Okay, so some of the textbooks use insoluble. However, in analytical textbooks we use sparingly soluble substances. That means they are not really soluble. However, at some extent they are. Okay, so we call the extent at which your insoluble substance will become soluble the molar solubility. Okay, so more on that later. So in order for us to answer equilibrium calculations, much advanced equilibrium calculations, we have to use an ice table. Okay, so an ice table is of course a table. However, um, we are going to track the changes in the concentration using this. Okay, so ice table stands for the initial, the change in the equilibrium concentrations. So we're going to dive further in how to use the ice table with this problem. So okay, so let's move here. So we have this problem. Isomers of stilbene have an equilibrium constant of 24 at 200 degrees Celsius given the chemical reaction. Okay, this is just an isomerization process anyway. So suppose there is 0.85 molar of these isomers. Calculate the equilibrium concentration of all the substances. Okay, what's noticeable is that we are given initial concentrations. Okay, not equilibrium concentrations. Okay, so this will require us the idea on how to predict the direction of the reaction. Okay, so anyway, so in order for us to answer this, we have to use ice table. Okay, so the initial concentration, change in concentration, and the equilibrium concentration. So how are we going to construct an ice table? Just write ice on the leftmost side. Okay, then after writing the ice, you're going to write the equilibrium reaction on the top of the table. So we have here, there's this isomer, there's this still being um, still being in equilibrium with the trans still being. Okay, then we are going to make columns per substances. Okay, so we have two substances, so I will make two columns. Okay, then what's next is that we're going to uh, plug in all the information in this problem into the table. So according to the problem, initially we have 0.85 molar of the cis isomer. This 0.85, I'm not going to write the molar concentration unit because it should be understood that the concentration is in molar. Okay, so looking at the question, do we have any concentration for the trans isomer? We do not have any information about that, so that will be 0. Okay, so after completing the initial concentration, we are going to apply the idea of the reaction quotient. Okay, so the idea we presented earlier is that the reaction will proceed to the side without concentrations. Looking at this problem, we have 0.85 in the reactant side and 0 for the product side. So that means that the reaction is going towards the product side. Okay, so how we're going to write it down, or how we're going to interpret that idea in the ice table? Since the direction of the reaction is going to the product side, that means the change in your product side will be positive x. Positive because it will be the concentration on the product side will be added. Okay, yx, we still don't know by how much, so by x value we're going to look for that later. So for the reactants, this will become negative x because our reactants will be diminishing to form the products. Okay, so x as well because we don't know yet what is the value of x. Okay, so that's the idea. For E, for the equilibrium concentration, we're just going to add I and C. We're just going to add them. Okay, so this is 0.85 minus x and x. So those are the equilibrium concentration of the cis and the trans still bead. Okay, so after writing the ice table, we're going to write down the equilibrium constant, or the equilibrium expression. So that is K equals the concentration of the trans isomer over the cis isomer at equilibrium. Okay, so what is the equilibrium concentration of the trans isomer? That is equal to x. What is the concentration of the cis isomer? That is 0.85 minus x. Okay, then the last thing we're going to do is that we are going to plug in the K value, which is 24. Okay, so I'm going to change this. I'm going to write 24 here. So what's next is that we're going to solve for the value of x. Okay, so this is just a little bit algebra. We're just going to cross multiply this. So we'll get 24 times 0.85 minus x equals x. We distribute 24 inside the terms in the parentheses, so we get 20.4 minus 24x equals x. And then we're going to transpose this to the other side. So that is 20.4 equals 24x plus x, or simply this is 25x. Dividing both sides by 25, we get x is equal to 0.816. Okay, so that means the changes for the reaction is 0.816. That means that the concentration of our trans stilbene isomer will be positive, or the change is positive 0.816. In turn, the equilibrium concentration is 0.816 molar. Okay, so for the cis isomer, that is negative x, or negative 0.816. 0.85 minus 0.816 is equal to 0.034. So 0.034 molar. So that means at equilibrium, the concentration of trans is equals to 0.816. Oopsie. It's 816 molar. The concentration of cis is 0.034 molar. Okay, so that is the final answer. Okay, it's easy for now. However, let's try the second problem. Calculate the equilibrium hydronium ion concentration from 1.2 molar nitrous acid given the equilibrium equation and the Ka. Ka is the equilibrium constant for acids. Okay, so we have the equation already. We're just going to construct the ice table. So that's I C E. So I'm going to copy the equation. Okay, so we have that equation. Okay, so we're going to make columns per species. Okay, so what's next? Okay, so we're going to plug in all the available information in the problem into the ice table. So according to the problem, we have 1.2 molar of nitrous acid. We're going to transfer that idea here, 1.2 molar. Then do we have concentration for hydronium ion? We don't have. Nitrite ion? We don't have as well. How about water? As you can see here, water is in the liquid state. Do we have to write water in the equilibrium expression? Okay, the answer is no. We are not going to write liquids and solids in equilibrium expressions. That means writing information about water here is not necessary, so I'll leave that blank. Okay, so after filling out the ice or the initial concentration, we're going to use the idea of the reaction quotient. Since we do not have concentrations in the product side, it means the reaction is going to the product side. Okay, so that means for the product side, that will be positive x, and negative x for the reactant. By the way, if you have coefficients in your chemical equation, let's say this contains 2, 2, 2, and 2. If you have coefficients such as that, we're going to multiply the value of x in terms of the coefficient. So if we have 2H and O2 there, that will become negative 2x. This becomes positive 2x, positive 2x. If this is 3, this will become 3, so on and so forth. Okay, so however, that's not the case. Oopsie. Okay, so however, that's not the case, so we'll stick with the coefficient equal to 1. Okay, so for E, we're going to combine I and C. So 1.2 minus x, x, and x. Then after that, we're going to write K is equal to the concentration of hydronium ion and nitrite ion all over concentration of nitrous acid. Okay, so K is this 7.1 times 10 raised to that. So let's write that 7.0 is 10 times 10 raised to negative 4 equals x times x divided by 1.2 minus x. So what can you observe? So just looking at the equation, we are going to use quadratic equations. Okay, so quadratic equation. So I'm going to copy this. Okay, so we have space here. Anyway, we still have space here. So I'm going to simplify the term. So that's 7.10 times 10 raised to negative 4 equals x squared over 1.2 minus x. Cross multiplying this term into the other side, that will give me 7.10 10 raised to negative 4 times 1.2 minus x equals x squared. So I'm going to copy this first. Okay. So after doing that, we have to rewrite the equation in the proper manner. What is the proper way of writing polynomials? You start with the highest exponent down to a number without exponent at all. So for quadratic equations, that means equations with x equal to, with the power of x being equal to 2, such as this one. So the proper format of the quadratic equation is a x squared plus bx plus c equals 0. Okay, so I'm going to do that. So I'll write 0 on the product side, x squared. Okay, then what's next? I'm going to multiply this and that. Wait, so by the way, let's simplify this first. Okay, so that's 7.1 times 10 raised to negative 4 times 1.2. That's 8.52 times 10 raised to negative 4 minus 7.10 times 10 raised to negative 4x equals x squared. After having this, we're going to rewrite this in this manner. So that becomes x squared plus 7.10 times 10 raised to negative 4x minus 8.52 times 10 raised to negative 4. Okay, so since this is a quadratic equation, we have to solve for the value of x. So what is the equation to be used? So this is the quadratic equation. You have to take note of that. Negative b plus minus square root of b squared minus 4ac over 2a. Okay, so however, I'm going to use the equation function of my calculator. So I know you know how to do this already. If you still don't, you can use online calculators anyway. Okay, so plugging in all in my calculator, I obtained the values of x being equal to 0.029. Let's use 4 decimal places. 88 molar. And the other root is negative 0.0295 molar. Okay, so we have two roots. The first root is a positive root, the other one is a negative root. Which of the following, or which of the two should I use? Okay, of course this one. Okay, so I'm going to use the positive root because positive root is the only root that makes sense. Okay, so we're going to get the positive root for this case. So since x is equals to 0.288 molar, that means I'm going to substitute that value of x into my ice table. So I'm going to erase this and write 0.0288, 0.0288. So what's 1.2 minus 1.2 minus 0.0288? So this is 1.1712 molar. This is 0.0288 molar and 0.0288 molar. So that, okay, that's how you solve for the equilibrium concentration.